Hello, everyone, and welcome to Echo Live. My name is Anna, and I'm coming to you from the Michigan Science Center's Echo Distance Learning Program. Today, we'll be talking about sink or float. It's one of my favorite science activities that you can recreate at home pretty easily using really any object that you choose. So if we're here to talk about sink or float, which is the name of our activity today, which is the general premise, basically, we're talking about density and buoyancy. Before we get started with our lesson, we have friends joining us through Zoom, through Facebook Live, and through YouTube Live today, which is so exciting. Since we have friends joining us on so many platforms, remember that your best way to communicate with me throughout the program is by using the chat feature on the platform that you're logged into. So right now, go ahead and introduce yourself in the chat. I'll be keeping an eye on the chat throughout the entire program to answer your questions and also so that I can ask you questions or have you make guesses or hypotheses about some of the experiments that we'll be trying today. So go ahead and type in the chat feature now. Tell me your name. You could tell me what grade you're in or maybe even where you're watching from. If you're watching from somewhere outside Michigan, welcome and thank you so much for joining us, and hello to all of our Michigan friends as well. We're so excited to see so many familiar faces. I see lots of friends typing in the chat that we see just about every weekday at 2:30 p.m. So welcome back and welcome to our new friends as well. All right, so if we're talking about sink or float, right, we said we are talking about density and buoyancy. So let's start by taking a look at an image which describes density. We've talked about density quite a bit throughout Echo Live. And this picture does a really good job of explaining this principle. Density basically means the amount of stuff crammed inside a set amount of space. So we have two equally sized cubes. So we've got a cube over here that's exactly the same size as this cube over here. But you can see that based on this photo or based on this diagram, there's a different amount of stuff packed into that identical amount of space. So even though their size is the same, their density is very, very different. So we have a less dense cube over here on the left, and the cube on the right is more dense, meaning it has more stuff or more atoms and molecules packed inside. So it's not about the overall amount of molecules, right? So if we were to scale up this diagram, right, we could probably fit more molecules inside them. We could also take some away, but we're talking about the same amount of space and just thinking about how these objects are affected based on the amount of molecules packed into it. One effect of density, right, is how it changes an object's ability to either sink or float. So there's a good diagram about that. And this principle we call buoyancy. Now, we've talked about Newton's laws a little bit on this program as well. If you haven't tuned in, you might be familiar with one of Newton's laws that tells us that for every action, there is an equal and opposite reaction. Now, that doesn't necessarily apply to buoyancy. It's not necessarily equal, right? Otherwise, everything would float. If the pressure down was the same as the pressure up, our buoyant force would keep our object right in the middle of the water. So buoyant force is pushing up on our object that we're either causing to sink or float, and the force of gravity is pulling down on the object. So if the force down on the object is greater, this could be because of that object's density or its weight, which is really dependent on what that material is made out of, right? If the downward force of gravity is greater than the buoyant force, that object will sink. But if the buoyant force, the force upward, is greater, that object will float on water. All right, so we're going to put some objects to the test. So I've got a tray full of objects here and just a large clear container of water. So you could very easily recreate this experiment at home using any objects that you're curious to find out whether that object will sink or float. So we'll go ahead and we'll pick an object. Let's first talk about these two objects right here. So I have two spheres or two balls. We have a ping pong ball, this orange one, and we have a golf ball, the white one. Right now they're approximately the same size, just like in that diagram that we talked about with density, right? So we've got objects of approximately the same size, but very, very different in density. So tell me, do you think the ping pong ball will sink or float? So again, this is a great time to use that chat feature. Tell me, think about the density of these objects, right? Think about how dense or how much stuff is packed inside a ping pong ball, and tell me, is the ping pong ball going to sink or is it going to float? Now I see a great question that popped up in the chat, so keep thinking about your answer, type it in the chat. And someone asked, is the force of gravity always the same? The force of gravity is always the same here on Earth. If we were to go to the moon, right, the force of gravity is much less, which is why astronauts can take such big steps or large leaps. But we have the same amount of gravity acting on all of these objects, right? But they all have different masses or different densities. All right, now I see a pretty unanimous decision, right? Let's go ahead and we'll drop our ping pong ball into our clear container. And you guys were right. This ping pong ball floats, right? Which means that buoyant or upward force is stronger than the force of gravity acting on this ping pong ball. All right, let's test the golf ball then. So even though they're the same size, we noted that this one is much heavier. There's clearly a lot more stuff packed into the same size sphere. So let's go ahead and we'll drop in the golf ball and let's see whether it sinks or floats. Look at that. Now you probably predicted, right, that since the golf ball is much heavier or much denser than the ping pong ball, right, that it was going to sink to the bottom, and you would have been absolutely correct, right? So it's all about density. Even though these objects are the same size, the golf ball is much, much, much more dense than the water even, which is why it sinks down to the bottom. When we talk about the density of water, it's about 1 gram per milliliter. So there's about 1 gram of weight to every milliliter of water. Anything that has a density higher than that, so 2 grams per milliliter or 5 grams per milliliter, or even 100 grams per milliliter, which would be really, really dense, right? Those objects will sink. Anything that is less dense than water, anything that is less dense than 1 gram per milliliter will float. So let's test a different object here. Now, this ping pong ball was made of plastic, and it did float, right? So plastic can be very lightweight. So let's pick another plastic object, like say this plastic, very small little plastic poker chip. So tell me in the chat, what do you think is going to happen to the plastic poker chip? It's pretty light. I haven't weighed it, so I'm not exactly sure of its exact weight, but tell me, is it going to sink or is it going to float? And someone asked, is this a grape? This is a grape. You can start thinking about that one. We'll test that one as well. I see that someone in Zoom tells me it could sink because it's so thin, but Kristen thinks it might float, right? So this object is extremely light, but go ahead and tell me in the chat. A lot of people are telling me float. A lot of people say float. A lot of people say float. A couple people say sink. Let's go ahead and put it to the test. So go ahead and we'll drop our poker chip into our water. Here we go. So our poker chip did sink, right? But you'll notice it sank much more slowly than our golf ball did. That's because the density of that poker chip is actually pretty close to water. It's obviously more dense, right? Because it did sink. But since its specific gravity or density is pretty close to water, we watched it sink through the liquid almost like it was molasses. Since they were pretty close in density, it sank very slowly to the bottom. All right, let's go ahead and test a different object. So I've got another plastic object here. I've got another bead. So this is just a plastic bead that you would use for bracelet making. Tell me, what do you think about the plastic bead? Think about what we've learned so far. I'll tell you it's pretty lightweight. Do we think sink or float? Sink or float? Tell me in the chat. Again, we're guessing for our plastic bead. Someone tells me since it's very light, it would float. Some people think sink, right? So it's made out of the same material as our poker chip, or at least it's made out of plastic, right? The bead will sink. I see a lot of people guessing sink. These are great hypotheses, right? So maybe we were surprised by the poker chip. I see some people say sink, some people say float. We've got a lot of great guesses here. Let's go ahead and we'll drop the bead in next. Here we go. 3, 2, 1. And that one sinks as well, right? So made out of the same material, right? So that should have been maybe a pretty good indicator that that bead might also sink. All right, now we've got some things that are pretty dense and heavy, right? So we've got things like this metal nut that, right, is pretty dense, pretty heavy, sinks right to the bottom very, very quickly, right? So since there's a much greater difference between the density of the water in that nut, right, the nut sank very, very quickly. Someone asked about the grape, so let's test the grape next. The grape also sinks, right? So even though grapes are full of water, there's also a lot of sugars inside it. And sugar is heavier than water. So the sugars inside that grape, even though grapes are mostly made out of water, will sink it down to the bottom. Now I have another really, really great question, depending on the temperature of the water. So this water is room temperature, so that its specific gravity is approximately 1. But you're right, that if you think that if we changed the temperature of the water, we would change the density, you're absolutely right. So if you were to recreate this experiment at home, right, to really turn it into an experiment, right, that means you need to change a variable. And one variable that you could change would be the temperature of your water. You could either choose to test things in hot water or maybe test them in cold water. And you could even test these same objects that I'm testing here. So you could test a grape, a golf ball, a ping pong ball, maybe a bead or a metal nut, and see if you can get different results by changing the temperature of your water. So we've got 2 last items to test here. We've got 2 cans of soda. So we've got 2 cans of soda here. Soda has a lot of sugar in it. And so we talked about the sugar inside grapes, right? That sugar is heavier than water. But we've got 2 different kinds of soda here, right? So we've got regular Coke, which has a lot of sugar in it, actually about 52 grams of sugar in this one can. That's a whole lot. So 52 grams of sugar in this one. But this one, if we look at the sugar content, it actually says 0. So Diet Coke has no added sugars to it, but it does have something called aspartame. And aspartame is an artificial sweetener so that it still tastes good without that added sugar. So let's take a guess. One of these is going to sink and one of them is going to float. And I'm seeing some people already starting to guess in the chat. Tell me, which one do you think is going to sink and which one is going to float? So again, we have regular Coke and we have Diet Coke. Which one will sink and which one will float? Tell me in the chat. What do you think? I have some friends in Zoom. Hello, everyone. I think we must have some people just tuning in now. So hello, everyone that's saying hello in the chat. We're guessing which of our cans of Coke here, which one will sink and which one will float. So someone asked, is there actually Coke and Diet Coke in these cans? There is. I've not opened them. They are completely sealed. So they are still full. I'll tell you that they're both very, very heavy. So even heavier than our golf ball or than our nut that we dropped down in there. These are very, very heavy. All right, so now we've got some great hypotheses coming in on Zoom and through Facebook. Someone again asked us to remind them about the difference between these two, right? Is that this one is full of sugar, which makes it taste so good. And this one is full of aspartame, which is an artificial sweetener. This one has sugar, this one does not. So we've got some great guesses in the chat. Let's go ahead and put them to the test. We'll start with our regular Coke and watch what happens. All right, so our regular Coke sank straight to the bottom, right? Somewhat slowly, right? Because there is a lot of water inside Coke. It's one of the main ingredients, actually. But those 52 grams of added sugar, right, made that liquid more dense than the water around it, which caused the can to sink. Now, just so we have some extra space inside there, let's go ahead and we'll pull out this can of regular Coke. set it back on our tray here. And now let's test the Diet Coke. And that one floats. So I think almost everybody in our comments got that one correct, right? The added sugars in the regular Coke, right, weighed it down. But aspartame is pretty lightweight. And so this is mainly made up of water and those lightweight gases, right? And we also have to think about that there is gas inside that can. Not necessarily that there's air inside. It's not that it's half full of air, half full of Coke, but there's carbon dioxide bubbles, which are what make pop carbonated, right? And gases are much lighter than liquids. So since there's no added sugar to weigh down this can, right, even if I were to kind of push it down, those gases inside and the light weight or density of that liquid are always going to cause it to float back up to the surface. All right, now we've got another experiment set up over to the side, and we're going to talk about another metal object. So we dropped one metal object in this container already. We dropped in our nut, which is pretty heavy. I have a penny here, so if we drop that in the container, penny sinks right down to the bottom as well. So metal is very, very dense. It's what makes it so strong and durable. But metal generally sinks, right? Because it is denser than water. So I have a different experiment set up over to the side. And for this one, we're going to try to overcome that density. We're going to try to make a metal object float on the surface of this water. So I have some paper clips here. And this is a really easy experiment to recreate at home. Now, obviously, if we take a paper clip, right, and we drop it into the dish, it sinks right down to the bottom. So it's definitely down there in the bottom of the container, sink flat down there really, really quickly, right? Because metal is more dense than water, more stuff packed inside each little amount of space of these paper clips. But there is a way to get these paper clips to float. To overcome that force of gravity. And we're going to do that using surface tension. So we talked about surface tension a little bit in our lava lamp episode. We talked about how water has polar molecules, that these water molecules really like to stick together. And so they kind of form a barrier between the water and the air. Now, if I were to take a paper clip, and I've actually bent this one open so that I can use it almost like a device to lower my paper clip down very, very slowly. If you do this very, very carefully, so you have to balance one paper clip on the other. If you then very carefully place this down in the water flat, so all at the same time, you can actually get the paper clip to float on the surface of the water. So we've actually overcome that force of gravity, right? Just by using the surface tension of the water. So we'll do that one more time. Use that surface tension. We'll float another paper clip down inside the water. And right, we said that the polarity of those water molecules is strong enough to float a really light but very flat object like a paper clip. But if you remember back to our lava lamp episode, if you were there for it, we know that certain things like surfactants, things like dish soap, are actually able to break surface tension. So if we take just a tiny, tiny dot of dish soap, drop that down on my finger. Now, if I were to touch the water with this surfactant, see what happens. Touch kind of near our paper clips here. Now, even though I didn't touch that paper clip, right, I didn't touch either one, that dish soap broke up the surface tension of the water. It actually interrupted those bonds, which caused the paper clips to sink. Now we've got another experiment using density set up for you. We'll switch our camera back to the front. And I'll show you this one. Now, this is actually from our lava lamp episode as well. So if you remember, we created lava lamps in that episode using food coloring mixed into water and then some vegetable oil. And we talked about that vegetable oil and water, they don't like to mix. And since the vegetable oil is much less dense than the water, it always floats up to the top. So let's move this experiment out of the way since we're done with our sink or float portion of our experiment. to our lava lamp here, we're going to add one more substance, which is syrup. So we've talked a lot about sugars in this episode already, and we know that sugar is super, super dense or heavy stuff. So if we open up our lava lamp, since we're done using it, I'm glad I've held on to it all this time because we can actually use it for this experiment now. I'm just going to take some syrup and squeeze it down into the bottle, and then we're going to wait for everything to settle. So here we go. You can tell me in the chat right now, actually, where do you think the syrup is going to end up? Will it be on top, in the middle, or on the bottom? So we'll end up with 3 layers here. So tell me, will it end up on top, in the middle, or on the bottom? Tell me in the chat what you think. See, some of our friends in Zoom are starting to send in their answers. Some people say the bottom, some people say the middle, right? So you're basing this question based off what density. Do you think that this syrup is less dense than the oil? Is it less dense than the oil, but more dense, or is it so less dense? Is it less dense than the water, but more dense than the oil? Or is it more dense than anything? If you don't know, that's okay too. Right? That's why we're going to show you this experiment live. So see some great guesses coming in through Zoom. Let's wait for a couple answers to come in. Oh, I see some great answers. A lot of people are telling me the bottom, the middle, right? So we're pretty confident that it is at least more dense than the oil, but we're unsure if it's more dense or less dense than our colored water. So a lot of guesses for the middle, a lot of guesses for the bottom. Let's go ahead and we'll just pour some in. All right, let's give it a moment to settle there. Add just a little bit more. Give our lava lamp a moment just to settle back into its layers. And we can see that the syrup sank all the way down to the bottom and formed its own layer. That's because that syrup is so much more dense than the water. Water is an ingredient in pancake syrup, but it's only a small amount of water in there. The rest of it is corn syrup and sugar, which sugar we've talked about is really, really dense stuff. So this is really easy to recreate at home. You could do it in any size clear container. And what we're going to do is we're going to try dropping a couple objects into our container here. So I've got a few light objects, a few heavier objects. We'll drop them in and then we'll see which layer they land in. So let's try to zoom in just a little more here. There we go. All right, so now that we're nice and zoomed in, let's go ahead and drop our heaviest object in first. So we'll drop another of those metal nuts, and let's see. That one sinks straight to the bottom, right? We can see it down there inside. So it's much more dense than even the syrup, and so it lands all the way at the bottom. Now let's try the grape. So we saw that the grape sank in water. So grapes are more dense than water. But let's see if they're more dense than syrup. So let's go ahead and drop our grape in next. And we can see that the grape is actually sitting on top of the syrup. You can kind of see it right here, especially if I move my hand around. So we can see that the grape is more dense than the water. So it does sink through both the oil and the water layer, but it lands on top. It will actually float on syrup. Then, of course, we have a couple other objects. So we've got our another of those beads. Ooh, and thanks to the surface tension of that water, right? That bead kind of sits on top of the water for a moment, but we can see that it's almost even right now, it's kind of slowly kind of sinking down to the bottom. It might rest there. Since we landed it pretty flat, it looks like the surface tension of that water is actually keeping the bead floating on the surface, but that bead is definitely more dense than our oil layer. We'll try something like a googly eye. And googly eyes, they're full of air. So we might be able to tell where this one's going to end up. That one stays right on the top. Since it's full of air, air is less dense than oil, water, or syrup, and so it floats on the very top. And lastly, let's try this plastic die. If it fits, there it goes. And our plastic die sits right next to the grape, so more dense than water, but less dense than syrup. So that is another experiment in density. We've got one last experiment to show you today. And this one is one of my favorites. Takes a little bit of practice, but this one is talking about changing that density of water based on its temperature. So I've got a couple of glass jars here. Now it's important for this experiment that I have jars that are identical, or jars at least that their openings are identical, that they're the exact same size. So I've got two small jars that are identical to each other over here, and two kind of somewhat larger jars that are identical to each other right here. So we're going to add cold water into one of the jars. And so I have some very, very cold water, and I put some blue food coloring already in these jars here before the program so that we can see it nice and well on camera. So we've got cold water. Again, blue is cold, at least when we're talking about water temperature, right? So if you think about which side of the sink gives you cold water, right? Normally we think of the blue dot or the blue marker as the cold side. So we've got cold water and cold water. And then I've also been keeping some warm water just off to the back. So this water is warm, not boiling hot. So you don't need boiling hot water if you were to try to recreate this. Warm water works just fine. So we'll fill the other jars with warm water. So we've talked about density, right? And throughout Echo Live, we've also talked a lot about how we can change our configuration of atoms and molecules based on their temperature. So that means that we're either adding or taking away kinetic energy. By heating up water, right? If you make water hot, you're giving those molecules a lot more kinetic energy. They're moving around, they're spreading out, and some of that water is actually even evaporating if it gets warm enough, right? On the other hand, the cold water, those molecules are very, very closely packed together. And so we've got two different temperatures, right? And so the molecules in both of these jars are very different from each other. So we'll start with this one over here. Let's see if I can zoom in on our beakers, or on our glass jars at least. Now you might remember this laminated card from our gravity fail experiment, somewhat similar in setup, but not identical. For this one, we are going to put the cold water on top. So to do that, right, we're just gonna seal the lid with the jar. We always do these kinds of experiments over a tray, just in case we spill a little bit while we set this experiment up. Which I almost certainly will. And then we're just going to balance these two jars on top of each other, which is exactly why it was important to choose two jars that are identical. All right, so our two jars are lined up on each other. And again, we have cold blue water on top with those molecules really, really closely packed together. On the bottom, we've got that warm water with those molecules maybe a little bit further apart, really kind of have a lot of energy to move. And then we're just going to remove the barrier between them. We're going to remove the card very, very carefully here, trying to keep the water as separate as possible. And look what happens to our mixture. Right? The blue water is very, very dense. Those molecules are very, very closely packed together. So we know that cold water is very, very dense, right? And so that cold water actually rushed down to the bottom. It mixed our two liquids together, which give us this kind of not as exciting purple color. But let's go ahead and let's try that in the opposite configuration. So instead of putting the cold water on top, in this experiment, we're going to leave the cold water on the bottom this time. So same setup, red is hot, blue is cold, but opposite orientation. And you tell me in the chat, what kind of results do you think we might see here? So take a moment to think about it. I'm going to go ahead and get our experiment set up. So I'm going to go ahead. Remember that for this one, right, our blue one will stay on the bottom this time, and we're going to set the red one on top and then remove the card. So make a guess. Tell me, will we get the same results? Will we get different results? If they're going to be different, right, tell me how. What might be different about our results? So go ahead and get this set up. We did have a little bit more spillage with this one, so good thing we have our tray there. Scoot it right into view of the camera. Now wait for your answers in the chat. So again, we're looking for, will we have the same results? So will we end up with a purple mixture? Will we have different results? And if they're going to be different, tell me how. All right, so we've got our two jars lined up very, very carefully, right? Hot water on top, cold water on bottom. See some great hypotheses. Some people are asking, maybe they won't mix this time. Will they stay separate? All right. I see some great guesses on Facebook. I see some great guesses on Zoom. Let's go ahead and remove the card and we'll see if you were correct. And would you look at that, right? Our two layers of water stay separate, except for, right in the middle, right? So water molecules are always moving, right? Especially in their liquid form, they're always flowing around. And so even though we have a small amount of mixture right here in this center zone where those where the two glasses of water meet, right? They're for the most part staying separate. And that's all to do with density. The blue water is much denser. This is not solid water, right? It's still liquid water, but it's so much colder that those molecules are very tightly packed together, which means that they are more dense than our warm water, and so they'll stay separate. Now, if you know a lot about water, you know that we also have this property called osmosis. And so water is always moving. We've talked a lot about diffusion in Echo Live as well. And so you might know that, unfortunately, these two layers of water, they won't stay separate forever. If you want them to stay separate forever, right, you might want to use a layer of oil and a layer of water. These eventually, over time, those molecules will mix together with each other. The hot water will cool back to room temperature. The cold water will warm back to room temperature, and we'll end up with kind of a uniform mixture between the two glasses. But for now, they'll stay separate for a good probably 15 minutes, which is pretty impressive. So this is a great time. This was the very end of our show. So if you do have any questions about density or buoyancy, please send them in the chat. I'd be happy to answer those for you. So send those in the chat. Thank you as always to our generous sponsors like the DTE Energy Foundation, to all of our other major donors who allow us to bring Echo Live to you at home every weekday at 2:30 p.m. Eastern. If you are enjoying these programs, make sure that you are liking and following the Michigan Science Center's Facebook page. If you're tuning in through Zoom, keep using that link. We will hope to see you everyone back here tomorrow and hopefully every weekday until at 2:30 p.m. Eastern. So if you're looking for guides on any experiments you can try at home as well, definitely visit our website, which is noted right here at the bottom of this slide. All right, let's see if we had any questions in the chat. My name is Anna, so good question. Thank you for asking in Zoom. My name is Anna. I'm here almost every Echo Live program, so I hope to see all of you back here. Now, Nakia asked a really great question on Facebook. She said, if we are heavier and more dense than water, why do we float? The answer to that is we are not heavier or more dense than water, right? Now, people sometimes sink or sometimes float depending on the contents of the water that you're in, right? So in really salty water, humans will float. You can also think about, right, if you take a deep breath and kind of hold it, right? Now you've got a lot of air inside your body as well. And so you can actually make yourself less dense than water by taking a big deep breath. There is air inside our body as well as water. And so you can make yourself float depending on the water's temperature and density with salt and other things like that. But as always, right, if you think to our surface tension demonstration as well, another great way to make people float, right, is by making yourself very, very flat. So if you take a deep breath and try to lay very flat on the surface, you can actually make your body float with very, very little effort. All right, let's keep an eye. If you don't float well, I understand that. It also has to do with your body content. So I know that people who are really, really muscular, they sometimes sink a little more than other people do. But that's okay, right? That's why it's very important to learn to swim if you're going to be in the water. Let's see. See a couple questions. Elise asked, can we do another experiment? Not today, but we hope we'll see you back here tomorrow. We'll be talking about sound energy and sound waves. I know that's a topic that people have requested in the chat before, and so we're very excited to bring you something that you've requested. So we'll be talking about sound waves and sound energy back here on Echo Live tomorrow at 2:30 p.m. Eastern. Thank you everyone so much for joining. If you do continue to have questions, please keep typing them in the chat or feel free to send us an email. We'd love to answer them. And of course, we hope we'll see you back here tomorrow at 2:30. So enjoy the rest of your day and keep experimenting. Bye.